All right, welcome to lesson 10.1 notes. Starting a new section here, new chapter on circles. Um, Chapter goals, chapter ideas here. Um, we'll get on the coordinate plane towards the at a couple different spots, looking at circles, looking at a lot of just parts of circles, properties of segments that intersect circles, and then some unique stuff that happens when we start throwing angles as part of circles. So let's do it. Let's get it going. 10.1 specifically. So we kind of touch on that first part where we'll introduce what is a circle, what are some parts of circles, and then some of these lines and segments that intersect circles. All right, so here we go. So a little bit of vocab. Definitely make the picture. This is all the parts that go with it. You can pause and add it. We'll talk through them here real quick. So definition-wise, what is a circle? It's our first figure of the year, our first two-dimensional figure that we're seeing that's not a polygon, right? We've done like lines, rays, segments, which were single dimension, but we've been a lot of polygons, quadrilaterals, mainly triangles. So a circle does not fall into that category. So by definition, it's a set of points on a plane that are all equidistant from a given point. So for example, we've got point P here. If you think about it, every point along this green circle, is the exact same distance from point P. And you start putting all those points together next to each other. Eventually, when you see enough of them, or there's an infinite amount of them, it eventually turns into what we see as a circle. Okay, so that's kind of what's going on there. That's what that definition means. So different than a polygon. The parts that I'm sure a lot. Well, let's talk about here. So a circle. How do we talk about a circle? We name it using the center. So this point in the center would make this the name of the circle, circle P. In abbreviation wise, we use just a little mini circle with the center in it, P. So we'd still say circle P using that abbreviation. Okay. So then the two parts. So the center is the point that we're equidistant from, point P. The radius is from center to a point on the circle. So it's a segment, and the endpoints are the center of the circle and then any point on the circle would be our radius. Diameter is essentially, we'll talk about this word in a second, a chord, but you could say it's a segment with endpoints on the circle. So maybe instead of chord, because we don't really know what that is yet, it's a segment with endpoints on the circle. So A and C are on the circle, but it passes through the center. It has to pass through the center, contains the center of the circle. So within a diameter, you have two radii, that's the plural. So radius AP, segment AP, and radius PC. When I put basically two radii together, I end up with a diameter. So lengthwise, a diameter is always going to be twice as long as a radius. So there's a couple just of the big things that, like I said, I'm guessing a lot of us had seen and talked about in previous courses. Yeah. One more, like we did this as a separate figuring class, then a little bit more circle vocab. These three, I would guess, are probably ones you're not quite as familiar with. Chord for one of them, but then two more. So let's take a look at the next one. A chord, what is that chord we were talking about? It's a segment whose endpoints are on the circle. So that's where diameter fits. It's just the diameter is a specific chord that passes through the center. So this is a little bit more bland, a little bit less specific. We just have to have our endpoints on the circle. So segment AB is a good example of a chord. Let's come over here to secant next in green there. So we're on circle F. A secant is a line that intersects the circle in 2 points. So you can see we've got line CD passing through the circle, intersects at point C, continues through the circle, and then hits again at point D, and then continues on. So the difference between chord and secant, a chord is finite. It's got a beginning and an end, points A and B endpoints. Secant, we're talking about the entirety of this line, so continuing forever in both directions. Within any secant, you're going to have a chord, right? So if I were to kind of ignore what's going on outside the circle here and here, we still have chord CD, a segment CD. So it's always going to work that way, where if you have a secant, you're going to have a chord contained within that secant. So the last one, which is the one we'll probably do the most with today, I know we will do the most with today in this lesson, is what's called a tangent. We've seen that word SOHCAHTOA, right? The TOA was the tangent part of it, so it's the same word. We're using it here in a context where we're talking about, could be a line, could be a ray, could be a segment. So we don't really have a way of naming this line right here. But this red line is what we would say is a tangent, in that it intersects the circle just once, exactly one point. It kind of just grazes and it hits the circle just in one spot. And we call that point a point of tangency. So point E would be a point of tangency. So that lays some of the groundwork, some of the vocab for not only the lesson, but for the chapter. We'll use a lot of those words kind of throughout. Let's take a look here at possible ways to look at how it would check some of your vocab comprehension. So we've got a figure, lots going on, lots of points, lots of segments, lines. So what I'm asking you to do is tell whether this, the segment, line, ray is best described as one of our vocab words. Okay, so we go through just making sure that we're focusing on, or you don't lose sight of, hey, segment, the abbreviate. It's been a while since we've worked with some of these abbreviations. This bar above the top with no arrows means we're just talking about segment BC. So from the center of the circle to the edge, we called that a radius. Or we define that as a radius. What do we got for the next one? Line EA, right? We said that makes a difference because sometimes that's how you distinguish between a secant and a chord type of thing. So EA, the line continuing in both directions, EA. I can see two intersection points at F and A, so this is what we would call a secant, intersecting the circle twice. We've got ray, DE, so it's a good chance to review some of our old terms going back to chapter 1. So starting at point D, continuing forever through E, looks like we end up with one point of intersection there, point B. So with one intersection point, we'd call ray DE a tangent to circle C. And then what do we got here? Segment FA. So back to a segment FA. So there it is. It's contained within that secant. We've got chord FA that we would call, segment FA. So that's just a brief look at how we, how to do a vocab check. It could flip, where I give you the radius, secant, tangent, chord, and I say use this figure to give an example of a radius. So you'd have some options: radius AC or radius CB. Segment, use the bars. Okay. Second example, radius, diameter, some of that length components. So use the diagram and the units to give the given length. So what is the radius of circle A? So just make sure it's a little bit. There's a couple different circles here on the page, obviously two of them there. I've got circle A with center right here. So whether I count up, down, left, or right, that would be the quickest way to find my radius. So radius from center to circle. So we could just say it has a radius of 2 units. Now the nice part is I could count for diameter. I could count 1, 2, 3, 4 units, but knowing that my radius was 2 units, we could also just double it and say, hey, you know what? My diameter is 4 units. All right, and then so we'll just basically apply those same concepts here to circle B, just making sure that I've got, I'm using point B to count to my circle. So north, south, east, or west, we'll go north. 1, 2, 3, 4. I've got a radius of 4. And if I double it, I should get the length of my diameter. We could count to double check, but I think we're all right. 1, 2, 3, 4, 5, 6, 7, 8. We're good. All right, so hopefully not making too big of a deal about that one. You guys usually do all right with stuff like that. All right, back to the notebook. A little bit more vocab. So now we start talking about circles within the same plane. So kind of putting multiple circles together. Let's start here. I'm kind of jumping around a little bit. So with this concentric circles, maybe add that as a vocab word. What are concentric circles? It's coplanar circles that have the common center. So you'd see something like this just as a picture. Where can I squeeze it in here? So for concentric circles, you would have a circle with a center. And then if I draw another circle with that exact same center, you're only going to see one. It almost looks like, in that case, like a bullseye, like a target. This is another example of right here, concentric circles. I kind of recreated that same picture. So you only see one center on the page. but two different circles. They're sharing the same center. So that's concentric. We won't do as much with those, but yeah, there's concentric. The other kind of um, concept that we need to see here going on is circles that intersect. So there's really three different ways that two circles could either intersect or not intersect. So let's maybe go reverse order. If two circles don't intersect, there's two ways that could happen. They're just two totally separate circles, or we have that they don't necessarily have to be concentric. You could have a situation where you've got that's supposed to be a circle and then another circle kind of inside of another. So that's an example of where it's just two circles wouldn't intersect. Two possible ways where we could have circles with a one point of intersection, and kind of the same deal where I've got one inside the other. They're just touching, they're tangent, you could say, at that point. Or you could have two separate circles, one outside, one's not inside the other, but they're just tangent at that one point. They just kind of graze each other. And then with 2 points of intersection, they kind of interlock. It's like interlocking circles. They have 2 points of intersection. Okay. So between those 1, 2, 3, 4, 5 kind of situations, you cover all the ways that a circle could or could not intersect. And then within each of these 5 situations, we have what's called a common tangent. So it's a vocab word. It almost fits right where we were doing circle vocab before. A common tangent is a line or a segment or a ray that is simultaneously basically tangent to two circles. So you've actually got right here, these two black lines are examples of what we would call common tangents. This black line intersects both the inner circle and the outer circle at the exact same time in one spot. Same thing here. This black line is intersecting this right circle and this left circle all at the same time, but only in one spot. So that's what a common tangent is. All right. So let's take a look. Next example. Tell how many common tangents the circles have and draw them. So we just looked at a couple. Where was that? Well, I guess we can start wherever. Let's start with part A. Why would we start anywhere else, I guess? So if I start looking here, and I'm basically looking, it'd be helpful with a straight edge. I don't have a straight edge here that I can use on the smartboard, but if I'm able to draw a line and just graze both circles at the same time with that line, that would be a common tangent. So right there, we just saw that one a second ago. Hopefully we're looking at this one saying, I think there's a few more actually, right? So if hopefully this one makes sense. If I were to drop this, and I'm doing the best I can to try to make it a straight line and not a lot of curves in it, but that line is meant to just graze here and here. That's a second common tangent. And then, we can get that same situation going on here on this other side where I'm just grazing here and here. And I think that's it. I don't know if, other than that, I don't think we'll be able to get tangent to both circles simultaneously. So this situation would have 3 common tangents. All right. Let's take a look at B. So I start looking here. Similar to the last one in that I can kind of travel along what we maybe think of as like the sides of the two circles. Okay, so one here and one here. The difference with this situation is that one that we would have had on the last one where we were able to kind of get through the middle here. Unfortunately, I guess it doesn't really matter, but I wouldn't be able to draw that tangent without hitting both circles twice. So we kind of lose that quote unquote middle one. So I would say this situation, we have 2 common tangents. Okay. Keep her moving. Part C, we saw this one on the previous slide where I was able to, you've got circles that are tangent just in that point right there. So other than that one point, I don't think there's just no way we're going to be able to get to this inner circle without intersecting the outer circle twice. Like, so for example, if I tried to get tangent to this inner one right there, I've now intersected my outer circle once. I would have to keep my line extending and say, oh, I hit it again. So that wouldn't be that one just not going to apply there. So I think 1 is all we can come up with there on this one. 1 common tangent. For part D, where I have that circle inside a circle, we just talked about it. There's just no way I can get a line to intersect this one at all without getting, intersecting this outer one twice. So we'd say here in this one, 0 common tangents. And then the last one, I like this last one. So you've got your 2 situations where these circles just don't intersect, right? There's no common intersection points between D and E. So you go from having 0 common tangents to, let's count them up. Oh, assuming we just hit once there. 1 common tangent. 2 common tangents. You see these ones? 3 common tangent and 4. So look at that. You go from 0 on the previous one to 4 common tangents. And that pretty much covers it as far as common tangents go. There's not another way we could arrange 2 circles. These are the 5 situations we just talked about. So yeah, there we have it. Common tangents. All right, a couple theorems left. We'll take a look. They don't have fancy names. Let's start here. It's just called, the book calls it Theorem 10.1. We in class put a heading on here, just called it radius tangent relationship. Instead of Theorem 10.1. It's up to you. I don't think that that's bad. It's just you don't need to remember that. Nobody's ever going to remember that this is called Theorem 10.1. But I guess it's important to understand, like, this is a proven theorem. This is true. So when we've got our circle in a plane, the line that's tangent to that circle at any given point would be perpendicular to the radius at that same point. Okay, that point of tangency. So to use another vocab word there, that if P is a point of tangency, our radius OP would be, perpendicular to that tangent at that point of tangency. So we kind of have to know what's going on there. If that's a radius, if we're told that line M is tangent to the circle at point P, then we would know for a fact that, hey, there's got to be a right angle there. All right, so that's one of our theorems. We'll look at a couple examples that, align with that. First situation here, making sure we pull apart the information. So we've got in the diagram segment RS. Where's segment RS? So that's my radius. Is a radius of circle R. So great, tells us it's a radius, fine. This is more of a question then. Is S segment ST, so this one here, is this tangent to circle R? So we don't know. So that theorem we just looked at told us, well, if this is tangent, that's got to be a right angle, but we don't know it is. So what do we have to do here? Going back to last unit, we're going to look at that Pythagorean theorem converse, and hopefully this is jumping out at us that kind of looks like a right triangle. With sides 26, 24, and 10. And this would be my hypotenuse length. So if this is a right triangle, what would have to be true? We should be able to take the legs squared and add them together. And like I said, if this is truly a right triangle, that should equal the hypotenuse squared. So we're using that converse of the Pythagorean theorem, 26 squared. I'm grabbing the calculator here, 676, just starting on this side. And left side, 10 squared, which is 100, I know that, plus 24 squared, I get 676 over here. So work-wise, explanation-wise, I think that's my evidence to say, hey, you know what? This must be a right angle right here. We just essentially proved it using that converse theorem. So to answer the question, I think we can get by with just saying yes. Segment ST is tangent to circle R. So kind of a combination there of, make a conclusion, and then we've justified it with work. Cool. So little Pythagorean theorem. Let's take a look here. Example 5. It's kind of the picture looks pretty close, but we'll see here. It's a little bit tougher. In the diagram, now it's telling us, hey, point B is a point of tangency. So it looks like this segment AB, if B is a point of tangency, this segment AB must be just intersecting at that one spot. And then it tells us the radius R, or that's what we're looking for, but this is my radius. So what are we going back to the theorem? The radius is going to have to be, it is perpendicular to any tangent segment. So this one's a little bit more, it tells us for a fact, like indirectly, that has to be a right angle right there. So initially, okay, sweet, this is awesome. It's kind of it's a Pythagorean theorem, I think, concept from the last section, or again, from last unit. If I take my leg, this would have to be one of the legs, R, so R squared, plus my other leg, big numbers here, 77 squared. Here's the issue. How do I know that this can't be my setup? Well, my radius my hypotenuse right now, 49, is smaller than my 77, one of my legs. So that's just out of the question. Like that one's not even close as far as the setup goes. So hopefully we didn't get too into that before you wrote it, or you didn't write it too much and start solving before we stopped. How long is my hypotenuse here? It is the 49, but then a plus an additional R, whatever that radius is. So we need to represent that in my Pythagorean theorem. We got to square the entire hypotenuse. So R plus 49 is a awesome way to talk about, hey, that's how long your hypotenuse is, R plus 49 units. So yeah, setup wise, I think we're okay. It's not really a question here. I shouldn't do that. Kind of clear this out of here. It's not a question that, like, this has to be true. This has to be equal. How do I solve this? So let's start with the right side, because I think that's the spot. What you cannot absolutely do is drop this 2 here and here. R squared plus, let's see, what's 49 squared? 2401. That is not a shortcut. Please, please, please do not do that. That's very frustrating. Okay, so what? Well, how do we do this? Well, what does to square something actually mean? It means to multiply it by itself. So we actually need to go a little bit old school here and multiply R plus 49 times R plus 49. So my guess is you did a lot of this in algebra. A lot of teachers refer to it as like a FOIL type of model. I'd say you're multiplying to a binomial, you're squaring a binomial. There's different ways to kind of say it here, but yeah, there's 4 different multiplications that have to happen here. R times R, which is R squared. R times 49, which is 49R. R times 49, which is another 49R. And then 49 times 49, we said it once already, was 2401. So those numbers do end up showing up, right? The R squared and the 24, that's 2401. But then so does this and this. These don't cancel out. So when it's all said and done on this right side here, the R squared is going to stay there. The 49 plus 49 is 98R. And then I've got my 2401. So it's a little bit of a process there, but we can do it. It's a skill that we should have become proficient with in an algebra class. Left side, I know we haven't really done there. Let's catch up. The R squared is just staying put. And then, yeah, at some point we got to do this 77 squared. So we'll grab the calculator and say, wow, that's a huge number, 5929. And it looks pretty scary right now, like all these squareds and huge numbers. But if we can get here, I would say, like, okay, we're almost out of the woods, because the first thing I would look to do to finish solving this is let's start combining like terms here. So if I subtract an R squared from both sides of the equation, if I didn't see it then, hopefully I see it now, that R squared minus R squared in both situations is 0, goes away. So it leaves us with 5929 on the left side of the equation, 98R, again, big numbers, but at this point it's a 2-step equation, 2401, it's a 2-step linear equation. Yeah, you create those squares for a second, the r squareds, but then they ultimately end up dropping out in this case. So yeah, let's do. Let's subtract a 2401 from both sides. It's going to leave us 3528 on the left side equals 98r. We'll divide both sides by 98 to get r equals 36. Holy cow, it came out perfect. Now, I'm not saying it has to always work that way. You could get a decimal answer, but 36. And yeah, it's totally checkable. I could come all the way back to the beginning, plug in a 36 here. Let's see, we'd be at what, 75? No, 85 for my hypotenuse here. So I could plug those numbers in and do a Pythagorean theorem converse check just to confirm it. If I thought maybe I screwed up somewhere along the way, but I like our answer 36. I think we're okay. All right, last concept. All right, one more short theorem for our notebook. We just kind of called this one in class. Again, it's another theorem. It's a provable fact or a provable statement, but we're not going through the proof of it. It's just, so for a heading, we put common external point. And it's kind of like the last one. We got to be a little bit careful here. This is what the theorem says, that tangent. So if we know for a fact that segment SR and ST are tangents, so tangent segments from a common external point, they would have to be congruent. So you kind of need some of that information. You'll see in the next example, there's quite a bit of actually information presented, like in the instructions and the directions. But here I think we're assuming a little bit that because it's the theorem that SR is tangent at point R, ST is tangent at point T, therefore SR would have to be congruent to ST. All right, so let's take a look. I mentioned it a second ago. Last example here. So here's what we got. It tells us that QR is tangent to circle C at point R. Okay, so that kind of takes care of this top piece QR. And then also QS is tangent to circle C at point S. So that's kind of a formality as far as, making sure that theorem applies. Now find the value of X. Well, what do we know? We know this is the exact same, that those are congruent. QR is congruent to QS, so their lengths would have to be the same. So it ends up being kind of a nice, small number, linear two-step equation to solve. We'll subtract a 5 from both sides. Divide both sides by 3 to get X equals 9. Could plug it into a quick check. 27 plus 5, yep, 32. So, and I don't want to minimize it as far as like work-wise go, but it's a little bit standalone. It's kind of just like hey, here's a fact. This is going to be true when those are tangents. So, yeah, that's the last one. So there we go. A little bit, we focused kind of towards the second half of the lesson. Common tangents, lines tangent perpendicular to the radius, and then tangent from an external point. So we focused a little bit heavy on tangent there for the lesson, but then don't also sleep on some of that vocab that we covered earlier. So I think as far as covering it all the special segments and lines, we hit all that vocab, and then we kind of went through some of those. Not even this one. I mean, we went through this one, but even more, a few other examples of circles involving lines tangent to them. So that's it. Done. 10.1 of the books. I'll see you in future lessons.